Okay, good. So I hope you enjoyed the coffee break. Waiting for more. Any question before I start? Yes.
Okay, yeah. So I was wondering, in this context, you last explained what exactly you mean by a gauge invariant charge operator. I mean, this is a like ungauged.
I mean, okay, charge operator is just the name I'm giving to the operators that are charged under the symmetry, so that they transform non-trivially under my symmetry operator. And with gauge invariant, I just mean that, yeah, this operator should be well defined in the sense that should be invariant under any other gauge transformation or diffeomorphism or any other local transformation I might have in my theory, that since they are redundancies, I mean, they should be preserved, right? So,
okay, so you're thinking about context in which something is gauged and something is not, perhaps. And so
I mean, if nothing is gauged, then okay,
right,
it's fine. I mean, this is not going to be a problem. But if something is gauged, this is what helps to distinguish.
Okay. Thanks.
Okay. And it's useful. I mean, the point is that when you just talk about the particles or the states, they are always gauge invariant, so you cannot tell whether the symmetry was global or gauge. But if you talk in terms of the operators that are going to create that particle, then it's different. They can be gauge invariant or not, depending on whether that particle will be charged under the gauge group or not. More questions?
Is there any contradiction between existence of global symmetries and gravity classically, or is this something that happens only when you try to quantize?
Good. So no, if it's completely classical, okay. So with classical, we have the gravity is sometimes a bit tricky, what we call by classical. It's about quantum level. The point is that, for example, at the semi-classical level, when you think of black holes and so on, you can already notice that there is something wrong. Because in gravity, yeah, like this notion of large distance, short distance, and everything gets mixed. It's like there's a UVIR mixing. But yeah, like in principle, this is about quantum gravitational effects. But that in some cases, you can already detect at the semi-classical level when thinking of black holes. Okay. But yeah, it's more like, I don't know, like with gauge symmetry, for example, something that another constraint that we know a lot is just that we are very used to it are anomalies. Like when you have a gauge symmetry, the theory has to be anomaly free. And that's the same that say that this gauge symmetry is preserved at the quantum level, right? And that should be preserved. The point is that with gravity, it seems that it's not enough just to require absence of gravitational anomalies to have a gravitational theory consistent at the quantum level. Unitarity of quantum gravity needs more things. And that's what we are trying to find out. Good. Okay, so let me just, what I was saying before the break, I'm just gonna briefly tell you this generalization, mention a bit the cobordism since it will play an important role this week. And then we will move on to the weak gravity and distance conjecture for the rest of this second part, which actually has many connections with the geometry of the compactification. So I guess some of the things will be much more familiar for some of you. Okay. So let me do it here. Just quickly to finish global symmetries. They are like generalized notions. Notions of symmetries. One is what I call this higher form, because it might appear during the week. So I think, I know, it's useful that at least we said the terminology, so you know what it means. So these higher form symmetries, sometimes also called P-form global symmetries. It comes from generalizing the dimension and the codimension of these operators, so that now they are parameterized by some operator U labeled by an element of the gauge group, of the symmetry group, but leaving now in a higher codimension space. Meaning that the operators that are charged and create the states that are charged under the symmetry are not going to be local, but localized on a higher dimensional surface. Okay. So now this has the right dimensions to link with each other, so I can surround these operators with this other one. And the point is that now the charges will be carried by p dimensional states. Actually, let's put brains. Sorry, p brains. Okay. So I have some extended object that carries the charge instead of just a particle. And this is something very useful because in string theory, we don't have only particles, as the name indicates, right? Like you have strings, you have membranes, and all these things and membranes are also charged under gauge fields, but they are p-form gauge fields, right? So that's part of the idealization. I have like some CP transforming CP plus lambda P, and I have all these higher percentages. Okay, just so you know, it's just a generalization of the dimension of the object. Okay, doesn't matter much. Now, the second one was non-invertible symmetries, which I'm not going to discuss here because I don't think we're going to have lectures on this. But just so you know, because it also connects with mathematics, like now we are getting rid of the idea that symmetries must form a group. It was always the case so far, but I mean, now with, precisely this language of talking about topological operators, many people think that, okay, maybe if I already have if I have some topological operator that does not satisfy a group law, what does it mean? In a symmetry? Do I have selection rules? I don't know, what is this? And this is also, there is a lot of activity here, which you don't satisfy a group law, but you satisfy some fusion algebra. Such that, yeah, when you multiply two elements, right? Here, yeah, you get like some structural constants. Let's put A and B, A, B. You have some structural constants, and here you don't have a single element, but a sum of several possibilities, meaning that these operators do not have an inverse necessarily. Okay, so
it's just some algebra.
It's an algebra, yeah, it's a different algebra. So it's not a group, but you can have a different set of rules. Why not? Right? And this is giving rise to a new notion of symmetry in that sense, and it's still underdeveloped to understand what are the physics consequence of having these operators. Okay?
Irene,
Yes.
the charged operators, both in the case to be local, 1 point, and in the surface, are unitary operators?
Yeah, these are all unitary operators. Oh, not necessarily. I don't think so.
This is funny, no? Because if it's not a unitary operator, this is not corresponding to really physically creating a perturbation which is charged, right? So what is the relation with the joint, with all that?
Why does it need to be? I mean, the symmetry operator doesn't.
No, the symmetry is a unitary transformation.
Exactly.
But the operator,
yes.
You are going to think that this operator is a physical operator. It's an observable.
Yeah, it can create. Yeah,
it can create something. Then it should be a unitary operator, no? Or in other words, what is the relation O dagger?
Yeah, I know. I'm not sure. I mean, I can check it out to be sure, but I don't think it's in the definition. I don't think it's.
No, it's physical question. You are defining operators in order to create here locally or in a hypersurface or wherever a perturbation that you consider that this is a physical perturbation with energy and charge.
Let me check it, but because my point is that I think with these new notions, I mean, sometimes I think it's not necessarily unitary, but let me not say it for sure, and I can let you know later. I don't want to put it in the definition because I think to remember it was not necessary, but I agree with you that then the physical.
Of course, this will be completely. It is not a unitary operator, can be whatever. And the second question is when you because you put O sigma p, this is defined by an integral or short or on the surface sigma p. What is the definition of O sigma p? Is integral over sigma p of something?
Exactly.
And this something, what it is?
Depends on this model dependent, right? Like now this is the operator that is going to create your p-brane.
Yeah.
Right. So it's going to depend on the gauge fields, like the TBI and certain so whatever fields are living on this object, what are the dynamical fields associated to it, we enter here.
No, the thing that confuses me is normally in local operators, as you know very well, you define some Schmeling function. Otherwise, this operator is not defined at all. It's simple. Now you have a support. Now you are Schmeling also around the surface sigma p or something like that.
It's like, for example, it's like one example. If I think that P is 1, is a Wilson line, right? Okay, if I have a 1-4 symmetry, then this operator is just the Wilson line. My field. And this is the operator that is charged under the 1-4 symmetry.
Okay.
That's just to keep an example in mind. So if this operator creates a string. And then the symmetry will be broken if this Wilson line can break. So you have charge states.
Now, related with the question of unitarity for these operators OX, for instance, if I am asking Irene, OX, OY commutator when X and Y are space-like, will be for you 0 or non-zero?
Yeah, just about the unitarity and the causality. Right.
Yeah.
Because the thing is that I'm including all these more weird things, and I think here you can make it work without that, but I cannot tell you now the physical interpretation, but we can think about it later. Okay.
Are there ineffective filters that may not come from a string theory? Do these higher form symmetries appear?
Yes, why not? As long as you have, I mean, it's difficult, which one, what do we mean? But yeah, you can think maybe I can put some higher spin theory in which I have higher spin states. Let's say I have, other extended objects. And you can have p-forward fields, like for example, there are some higher spin theories in 2 dimensions, that non-Vasilic theories. It's not very clear how to get from string theory yet, but they are higher spin theories. And they have, and whenever you have higher spin, it's because you can think that those states are excitations of an extended object. So you are going to have all these p-form higher possibilities. Of course, we know this better in string theory, but why not? It's like possible representations of Lorentz that you can have higher spin. So it is going to be correlated to this. Okay, and then the last thing, which it's gonna be more important for this higher form for this week, is the covariations. Okay, the covariation classes. So the point is that so they are associated to some current is just F with some the curvature of my connection. Okay. The thing is that these are topological invariants. So the covariation classes are really related to topological invariants you have in your manifolds. And it goes beyond that because it will allow us to think of charges that are not necessarily associated to gauge field or scalars or particles, but to gravity itself. Okay. So the way, I'm just gonna define it quickly because you will hear much more about it, but at least to get an idea. The point is that, well, first, for those of you that do not know, covariism is an equivalence class. Okay, that if you have some manifold of dimension D and another manifold of the same dimension, okay, these two are coordinate to each other. If I can write the union as the boundary of one dimension more. so that this forms a group, okay, which when the operation is just the union, and the trivial class is the case. The trivial class is the case in which a manifold is a boundary by itself of another one. So this is what forms this coordination group, in which you are fixing the dimension of the boundaries. Okay. And Miguel will explain this much better on Thursday, but the whole point is that if you have different classes, okay, so now this is an equivalence relation, so we can have different coordinating classes, or we mod under this equivalence relation, and different, if I have some different equivalence classes under this coordination group, are conserved charges from a physicist perspective. Because if I have different classes, it means that I have some manifolds that I cannot connect with each other. Like what I'm doing here is that I'm connecting like this one with another one by going to one dimension more. If they are on different classes, there is no way to connect them, which means that I have some label. There is something that distinguishes them. And this difference between the manifolds is a conserved charge. It's something that cannot change. And it's a conserved charge which is global. It has nothing to, it's not associated, right, like HP or diffeomorphism or anything like that. It's a topological charge. So different equivalence classes corresponds to different global charges. And in quantum gravity, since we think that there are no global symmetries, implies that this coordinating group must be trivial, in the sense that everything should be connected to each other. There should not be a quantity that distinguishes one from another, because this is like some invariant. Okay, this is a bit this is the intuition.
So
Okay.
In particular, it means that everything should be a boundary. So everything is connected.
Maybe combined with another one. So yeah, like union. So yes, in the sense that you can always connect any manifold. You can connect it to another one. So the union of this one and other ones should be a boundary of another thing. Which means
the unit element is always there, right? Like which is the boundary of something. And if you can always connect it to the unit element, that means that
exactly, yes, exactly. Yeah. So everything exactly in the end, everything is a boundary because everything is going to be on a trivial class. Yes. Okay, so everything should be able to end. And this has, okay, let me mention two things. So from if I think of that I have string theory and I compactify string theory on these manifolds, okay, on C or on D, right? Because my compact manifold that I compactify string theory, I get some low energy EFT in 4 dimensions, okay? And I have another option, which is compactify string theory on this other one, okay? And I get a different EFT. I have EFT1 and EFT2, and two different theories in lower dimensions. What this is telling me is that since they are both the boundary of another one, since I can connect them, this represents, from the low energy perspective, is a domain wall, right? So this has 1 dimension more, so this is a domain wall connecting the 2 EFTs. Okay, it's like an interface. So it means that all the effective field theories, all the theories that you can get from quantum gravity, from string theory, somehow should be connected to each other in the sense that there should be some finite energy domain wall associated to this manifold. This has finite volume, this finite energy, such that if I cross this domain wall, yeah, I'm in the other EFT.
Is the base the space of CFTs or is the space time? The base in the picture?
This is space-time. This is non-compact space. And this is the compact space. Okay? This is the non-compact space. This is the Minkowski 4-dimensional space. So from this non-compact space, this is a domain wall.
I'm a bit confused about your argument because so when you talk about no global symmetries, your argument was about effective theory in 4 dimensions. And now you are saying that you are applying this to the compactification, not to the effective theory downstairs. So you have said that if the
no, wait, this covered this in class from the dimension of the lower dimensional theory. It actually gives rise. Let me write it correctly. D minus P. Yeah. It's if I start. We start in 10 dimensions, or what, like a higher number of dimensions. D10 minus, we put here D minus 1 form global symmetry. So it gives rise to these higher form symmetries here. And that's because like this, if you want, can see like these domain walls are charged under it. So it's like this is the object that is going to break the symmetry. So it's a higher dimensional object. And that's why the symmetry associated to these coordinate classes typically are like higher form symmetries. So you have two options. You can think of it just as before, from the perspective of the non-compact space, where you live, and space-time. And then you can distinguish, sometimes, I mean, you're gonna have some this symmetry that you can check. Sometimes it's more difficult to check because it's really associated to gravity and it's hard to formulate it, but I mean, it should be possible. Or you can think from the total space where I'm coming from, and that I also have some internal space, and then the fact that this symmetry is broken here is equivalent to say that I can deform the charge into another one so that I can connect the two theories, meaning that this manifold can be deformed into this one. So there is nothing particular about one, there is no invariant. So it's going beyond topology. I mean, this is about like this, even if these two manifolds, and here I can have topology changing processes that connect the two manifolds. It's not just a smooth deformation. It can be completely different topologies. But if I can have some topology changing processes that go from one to the other, then that chart is not conserved anymore. And that's how you break this.
Probably you explained in the previous talk that I was not here. Topological charts, because an example of covariation is just homotopy.
Yes.
Trivial example, if you want. Then topological charts associated to homotopy classes are not conserved when you introduce quantum gravity, for instance, soliton number. I give you a theory with solitons, and the chart of the soliton is simply the homotopy class. Sorry?
These are like the magnetic charges, right? When you have the gauge field.
Can be magnetic, you want to call it magnetic, but imagine a theory of scalar fields.
Scalar field.
This is broken in quantum gravity?
It's like every, if I think of the top lines, for example, no? Or like it can have like some, I need to have magnetic monopoles.
I don't think in magnetic electric, just imagine a scalar field that you have a king, okay? And the homotopy class, by one or by whatever, you have a number n, which is the topological chart. You say that the topological chart is not conserved when you couple this thing to quantum gravity. But why?
Because you have something that allows, some physical process that allows you to deform that charge and get rid of it. So,
and this, for instance, is because one example, obvious example, is always baryon number. Now, if you look into the infrared, you can use to characterize baryon number the Skirman model and it's a topological chart. The baryon becomes a topological chart. This was the original work of Mr. Witten many years ago. You say that when you couple this sigma model to gravity, this topological chart is not conserved? Sorry?
There should be a way to break it. Typically, I mean, you can also gauge it. I mean, you can also try to gauge these things. But typically in a string theory examples is broken because you have states that are charged and are going to break this extent object. And here, from this perspective, like I mean, what you said before, everything is on the trivial class, which means that everything is a boundary by itself. So you always have also like some end of the world brain. It's like can spring to zero. And this actually is also very important because all this end of the world are also playing a lot of a very important role in string theory and stability. We can discuss later more detailed examples. Okay? Just, I mean, I don't want to get into a lot of details here because this is like Miguel lectures and other people will talk about this in detail. I want to give a little intuition so that when they start talking about it, you know where it's coming from. Okay, it's not that you put just because, it's because in principle this is associated to some global symmetry that you want to get rid of in quantum gravity. And this is one of these corners in which a lot of mathematical, math and physics are going at the same time. And so that there are many developments here with these coverage classes that are starting to be very useful also to classify many things in string theory. Because of requiring this, which is really non-trivial to require this. Okay. So, if I mean,
yes.
So you have some question?
Yeah, just one thing yes too. So your argument about trivial coordination group, you're applying it to 10 dimensions in your picture.
Whatever.
Yeah, it's not applying any dimension.
Okay.
Right now, I'm thinking of starting with 10 dimensions just to make it a bit concrete. Compactifying in a d-dimensional compact space and getting space-time. But yeah, probably Miguel will say, like in general, one is trying, like this is very well defined because here really connects with this element in geometry that we can talk about, like this covariance class and so on. More generally, one thinks of like a covariance on quantum gravity. It's more difficult to define, but to include any global symmetry in any dimension. Okay. But in this case, it's very well defined, and it really connects with something that is well defined in mathematics that one can check. And what people are doing is that since you have to require this, I mean, sometimes maybe you get that this is different from zero, you get different classes, but that is typically a hint that you are missing something. And like, for example, if I start with a string theory and I have gauge fields and I have fluxes and so on, I'm gonna get that this is different from zero because these are gonna, like the different gauge fields are going to have here the topological invariance associated to the connections are going to imply that this is different from zero. But what this is telling you that you're missing something. Well, what you're missing, for example, are the presence of branes. So the presence of branes are going to trivialize this group. So people are using this to predict the existence of new effects in string theory, such that in the end, you get that this is zero. Okay? And it's very powerful because it's becoming a new way to predict even non-supersymmetric effects, which in string theory is very difficult, and so on. There's research here. So trying to, and how to compute these things is also non-trivial, and that's why we're trying to learn from the mathematicians how to do it. Because if we learn how to do this, more complicated, like here, don't discover this in classes, then you are going to trace them with some structure. This might have some spin structure, different structures, and how to compute these things can get cumbersome. If you do it, then it's a tool to classify the possible IFTs that you can have in lower dimensions, the possible theories that you have, and also predict new effects. So it's very important. Okay. Any last question? Yes.
So for compatibility with gravity, is the statement that these the compactification manifold has to be a trivial cobordism class or
yeah, has to be trivial.
But like
how that happens?
So it means that like okay, so in string theory you have Calabi-Yau three-folds, and it's basically saying that the Calabi-Yau three-fold is always a boundary of something. So
yes. It's that. So that means that here, what I said, you might need to include more things. Like if you just take pure Calabi-Yau, it's non-trivial. But if you put a Calabi-Yau with branes, fluxes, and so on, and things that you need by consistency or tupole cancellation and other things, then it should become trivial. So after taking into account all the string theory and all the quantum gravity, this is like telling you, okay, I put string theory on some manifold, but by consistency with quantum gravity, I need to have ingredients, I need to have things, or I need to have some defects, or maybe not any manifold is allowed. So which one is allowed, what ingredients are allowed, in combination, everything should be such that.
But there's not something that I'm putting in by hand, right? It should be an outcome of.
It should be an outcome, yeah, of course. I mean, if this is true, right, it should always happen for any consistent string theory compactification. Or in a global symmetry, how approximate they can be. Okay? And this is important in physics because, yeah, like maybe, as I was telling you before, like we discuss everything in terms of energies, and if I am here at low energies, and I tell you, okay, here I have some symmetry which seems exact, but actually I'm gonna have some effect at very high energies that break it. That's enough with this because it's broken in quantum gravity, so that's enough. But maybe it's not very useful for someone doing experiments here because this effect might be negligible in a sense. Okay, so it's important to quantify how much we have to break the symmetries to be consistent with quantum gravity. And this is what the other lectures that in the rest of the time I'm going to discuss aim to quantify. Okay, so I put you before the weak gravity and the distance conjecture. It's well related to no global symmetries in the sense that they quantify like how much you have to break or get this. Okay, so let me give you the definitions. Okay. So we have the weak gravity conjecture, which states that if you have a gauge field, okay, you have gauge the symmetries, fine. That's not enough. So given a gauge field, a gauge theorem, that is coupled to gravity, you must also have states that are charged under it. So you cannot just have the gauge field alone. You must have charged states that is fine. And the charge of the state over the mass of the state is bigger or equal. And the charge to mass ratio, the charge of the mass that a black hole, an extremal black hole has. So this is like some order one number, okay, that I can compute in my theory. So basically what this is telling me that I need to have some states in which the gravitational interaction is weaker than the gauge interaction. So the charge is bigger than the mass. Okay. Now, why is this? Well, we spend a lot of time providing motivations. Since we were discussing our global symmetries before, maybe a way to connect this is that this gauge charge, okay, is a quantized charge times the gauge coupling, in the sense that if this becomes very small, okay, I am in a situation in which I am close to restore a global symmetry, because the gauge coupling is the, right, if the gauge coupling is 0, it means that the gauge field does not propagate anymore. So the symmetry that was global and now I get becomes global again. Okay, so the limit in which the gauge coupling goes to 0, I restore a global symmetry. So something should go wrong then. Okay, I should not be able to take this limit in quantum gravity. And what is going on is that when you make this gauge coupling small, you are also going to have states that become light. Okay, so you pay a price. And in the limit, they become massless. So like the theory that you had before, I mean, stop being valid. Okay, I have to worry about it. So there was some motivation also coming from black holes that you can argue that you need this for the black holes to be able to decay and other things. I think I'm gonna skip that. Because we don't have much time. I think it's important then to get to the connections with the geometry and the manifolds to connect with the mathematicians. So let me just point out that the point is that, okay, this is the conjecture. You can also motivate it with black holes. But what we observe in string theory, I mean, all the string theory examples always satisfy this, but satisfy even a strong version of this. In the sense that you don't have just one particle satisfying this, you have infinitely many. You have a full sublattice or tower of states satisfying this. Okay, so in string theory, we get we call a sublattice, so you can just think of the possible representations under your gauge group, and this is form some lattice of charges. So what you get is at least a sublattice, so you're gonna have infinitely many, or a tower in the sense that you have like infinitely many states with different values of the charge, okay? Heavier and heavier, satisfying the movability convention. And this connects with what I said before, because if you don't get just one state becoming large, but you get infinitely many of them, then of course the theory that the model that you were using doesn't make sense anymore. Now you have infinitely many more states to consider, and you cannot keep a weakly coupled description of gravity. So quantum field theory breaks down, and that's where, I mean, only in quantum gravity we can make sense of having infinitely many degrees of freedom. Okay, so the point is that as the gauge coupling is very small, I can think of a cutoff, which is like the energy up to which my model makes sense, the IFT makes sense. So this cutoff is going to 0. In the sense that I get more and more states, and at some point I cannot make sense of a theory with infinitely many fields in quantum field theory. I need to go to quantum gravity and understand what is the resolution of having all these states. Okay, so the quantum gravitational effects become important, and they do not allow you to restore the global symmetry. Okay, this is the physics intuition.
Can you say by words again the statement of the weak gravity conjecture? So there are some charge states, just that the charge divided by the mass is bounded by.
Yes.
By what? Some prescribed.
Yes. So this is it's bounded by the value of the charge mass ratio that a black hole, that an extreme black hole has in that field. So the thing is that some of the motivation comes from black holes. That's why this enters here. I'm kind of skipping that because of lack of time. But the point is that you have a given theory, you can compute the black hole solution in your theory, and then you can know what is the possible. So whenever the black holes are charged, for each for a given value of the charge, there is a minimum mass that they can have to have a black hole solution with a smooth horizon. And this minimum value is what we call extrema, is the one you saturate. So this is an order one, this is a number in your theory. So given the theory, you can compute this number, which is the charge ratio of a black hole, which is extreme, which is the minimum, the black hole with the minimum mass that you have. And then the statement that you need to have states that have a charge ratio bigger than this.
So if you have a field theory, will you find the states which
doesn't mean that all the states must satisfy this? Okay, not all the states, but some states must satisfy this.
Yeah, what I'm saying to rule out something which does not come from quantum gravity. If you find that all the states, the charge divided by the mass when you go to the infrared go to zero, then this cannot come from quantum gravity.
Exactly. And I mean, this is to allow black holes to decay because otherwise they will remain stable. You can also run troubles of remnants and other things. And it's because, the more that it's covering, the more similar the black holes look again. You will get into trouble unless they are able to decay. There are different motivations in physics, but the point is that you need to satisfy. I mean, this is, if you have this, then kinematically these black holes will be able to decay and they will not be stable and they will not count as different states. And
is it enough to look at the extreme of black holes to check the? Can you just?
You mean if these can be black holes themselves? That's despite.
Yeah, if you check.
Exactly. So the point. So here so this is the statement, but the research here is that the conjecture itself is not telling you, who are the states satisfying this. You know that you need some, but you don't know which ones. Okay, and it could be like from the motivation of black holes and so on, it could even be that these are like very small black holes that are already allowed satisfying this, so it has nothing to do with particles or something used to do with phenomenology. But what we observe in string theory, so this is where string theory comes. In string theory, we can identify what the states are. We have the spectrum and we can check. And so far, in all examples, what we find is that indeed you have infinitely many states satisfying this. Okay. And they are, they always have some structure in the sense that, like you have some sublattice, some tower of the states. So that when you integrate them in, like when you consider them then in quantum gravity, for example, they are going to correspond to Kaluza-Klein copies, or we're going to see they have some meaning. Okay. So the most important, the thing to understand with the gravity conjecture is also, like to understand who are these guys, how to identify them. And the most important thing, exactly, like what is if I have many of them satisfying the conjecture, the lightest one, the one that has the smallest charge, who is it? What is the minimum charge of the state that has to satisfy the gravity conjecture? Okay, so the minimum value of the charge, how small it is. Because if I wanted to use the phenomenology, this has to be quite small, so it really corresponds to a particle that I can measure in experiments. So what is this minimum value? And how to find this? You really need to keep track of all these states, like to understand the spectrum, and this is where all these modular forms and so on are going to become important. Because sometimes, for example, these states satisfying the gravity conjecture will appear as excitation modes of some strings and Zenith objects, and how to quantize the strings and understand how many charge states I have and what is the minimum value of the charge requires well, understanding modular properties of viscosity coiforms and many things that we will learn about this week. And everything is about, like to be able to show that it's not just one state, but to really be able to count how many you have and what is the minimum charge. Okay, this is the main question for the duality conjecture.
One question. So you said that in principle there could exist states with a smaller charge to mass ratio than the.
There could be others, yes.
But
not everything.
If there is something with a smaller charge to mass ratio, it could radiate off the mass that it has until it gets to the extremal point back, right? Like so.
Say again?
Like if there is something with a smaller charge to mass ratio, it will radiate off. Like it's not. Is it?
So let me put. So typically what happens if I plot the charge and the mass of all my particles is that I have some geometry bound. In the sense I'm telling you that I need to have some states below this, that the charge is bigger than the mass. And black holes like here, extremal black holes right here, this is the extremality bound. And the point, what one observes is that as you start going to smaller masses and charges, even small black holes, like people are trying to prove the gravity, like studying already this region. You can show that small black holes, the corrections move you in this direction. And the question is, if you continue, like and I have more states here, I might have some here as well, but I must have some here. What is the minimum charge of the smallest one that is below the line? And maybe here I have just some states, but for example, the electron, I can tell you that the electron in our universe satisfies this by a lot, like 10 orders of magnitude. Okay, so the electron satisfies the gravity conjecture. It was on mix, but with us. Okay, this is entanglements. And we think that because of consistency with quantum gravity. Okay, so this is constrained the spectra of your theory. Okay, and the point is that in the string theory, all these charges and masses, right? We will determine these things by studying volumes of cycles, and there is a correlation between the different volumes of the cycles, and so that you can satisfy these things. So it really translates to geometrical properties of the compactification.
So why is the evidence for weak gravity conjecture? Can you explain what it is, but why we?
So the evidence is, so there is a heuristic motivation from black holes, the same as with global symmetries, but this is kind of motivation. Then the proper evidence is that it has been, well, all the string theory examples satisfy this one. It has been proven in the worksheet. This is in string theory. You can, it's like you have the strings propagating in a worksheet, and then it has a space-time description. So whenever the gauge field has an interpretation in the worksheet, you can prove the gravity conjecture using modular invariance from the worksheet. So that's kind of aesthetic, which means that it's also proven in holography when you have ADF3, CFT2, because again, modular invariance, here you have the modular invariance, and you can relate this to the gravity conjecture. And also, there are other connections with other properties like unitarity and causality that you want your scattering amplitudes to satisfy. You can try to argue that if you want in higher energies to have a unitary theory, maybe in lower dimensions mean that you need to have this particle. Different types of arguments coming from different areas. Also, other arguments related to weak cosmicity of C, which is another statement that there are no make singularities in gravity. It's related to this. But mainly, I would say, as usual, most of the evidence comes from string theory. From what we know about the compactification and about the analysis in the worksheet in string theory. Okay. Yeah, I know. Sorry. Okay, let me quickly, because I'm running out of time, let me give you also the definition of the distance conjecture and then we finish. Sorry, I cannot discuss in more detail, we went too much with the global symmetries, but it's very connected to this one, okay? So the whole point here is that now this has even a more geometrical picture in the sense that, okay, I said here, okay, if the gauge coupling is small, what does it mean that? I mean, how do you do this? So the point is that in string theory, all the parameters, there are no free parameters in the sense that everything is parameterized by the Banking expectation of some scalar fields. So what happens is that when we compactify, right, we compactify on some manifold, we have some modular space, okay? That maybe then we can stabilize with some field space, but the point is that different points in this modular space from my compactification correspond to different values of the parameters, the gauge coupling and the masses and so on. So they are like different effective field theories. And I can move in this modular space, okay, and probe different effective field theories. And the limit in which a gauge coupling becomes small, so the gauge coupling is going to change depending where I am in this modular space. So when a gauge coupling becomes small or I restore a global symmetry, what is happening is that I am pushed towards an infinite distance boundary of the modular space. Okay. So now, instead of talking about masses, gauge couplings, and all these physical quantities, we can talk just about pure geometry of the modular space. You can say, okay, I have some compactification of string theory. I can study what is the modular space of this compactification. And whenever I move to an infinite distance singularity, an infinite distance boundary of this modular space, something has to go wrong because I'm going to restore probably some global symmetry there. And what goes wrong, I mean, what happens, I mean, something new appears. What appears is that there is an infinite tower of states that become light. In particular, they become exponentially light. So imagine I start at some point P and I move towards some point Q, okay, in this modular space. So the mass at Q is given by the mass at P with this exponential drop-off, where delta phi is the geodesic distance that I travel in the field space. Okay, so this is geodesic distance. Become light as this geodesic distance goes to infinity. Okay, so I move, if the statement is that in a consistent theory of quantum gravity, I can check what is the modular space. That's, I can also think of from a physics perspective, I have some scalar fields, I have some kinetic terms for these scalar fields. The field metric is a metric in this modular space. I have some scalar manifold. If I move in this scalar manifold parametrically far away, I must have an infinite number of states that become exponentially light in terms of the geodesic distance that I travel in this field space. Okay? Is it clear? And actually in all the examples so far in string theory, these two conjectures come together because it seems that we always, whenever we move to an infinite distance boundary in string theory, there is always, it seems that we always find also some P-form gauge coupling that goes to zero. So it's also a weak coupling point. Meaning that these states, I mean, I can find towers of states that are also charged under the gauge field, and that they satisfy at the same time both conjectures because they become exponentially light on the distance, and if you check it, they will also satisfy the weak gravity conjecture. Okay, so it's the same tower of states satisfying both things. It's just that here you put the emphasis on the scalar field variation, while there you put the emphasis on the charge, on the gauge.
So what is the little m, MQ, can you say that?
Little
the MQ, MP, what is
This is the mass. Okay, so the mass of the states must behave this way. Okay, so it's
so
given.
the little m is the same as the big M.
Exactly. Yeah, sorry, maybe didn't remember what it was. Yeah, let's put here.
So they are essentially the same conjecture.
Depends. I mean, if you're asking me. So it's okay. Here, the point is that this is just based on an example. I mean, I don't know if there is any fundamental reason why every infinite distance limit should be a weak coupling point. If I assume that, then I'm gonna have a triangle satisfying both, and then become equivalent. Of course, the quadratic conjecture is also valid in the middle of the space, but in the middle of the bulk, I cannot count. I mean, since it's not weakly coupled anymore, like counting how many states I have is not well defined. So counting how many states you have and talking about a tower as a lattice is also something that is just well defined here typically, where you also have the distance conjecture. So at least my expectation is that here you still satisfy the gravity, maybe you satisfy them with black holes, but as you approach a weak coupling limit, the states that satisfy the quadratic conjecture must become light. And they really correspond to particles, and then it's the same like this. It's my perspective. Okay, so this is something which is, yeah, this is something that really is giving you a relation between the spectrum, your theory, and the moving, like the distancing, no, like the geometry of your modular space. And this is what also, like, yeah, there has been a lot of, I mean, works like that will try to prove this. Like, for example, for any Calabi-Yau manifold, like you can, it's a matter of classifying what are the infinite distance boundaries. It becomes a classification problem. You can take some large class of compactification, like for example, Calabi-Yau compactifications, and you can aim to classify all the infinite distance singularities that you have. And then you have to show that for all of them, regardless of the Calabi-Yau manifold, regardless of other detailed properties, for every infinite distance singularity, you find these states, which is going to be related to what is the geometry near here, because the mass of the states are like volumes of cycles. So it's about how the volume of cycles behave, right, as you move to this non-compact
directions. Do you allow topological change in the Calabi-Yau when you go to the boundary?
So I can have, here there is no need, like it's true that, for example, you can have finite distance singularities in which you have some topology changing process, like you can connect different Calabi-Yau with some flux transition, but these are typically always finite distance. When you have a topology change, it's finite distance. You go to infinite distance, it's not just our topology change, it's something much more drastic, because you really have an infinite number of states, which means that this description, you cannot make sense of it in quantum field theory anymore. And then, so far, there are two options. So you can say, okay, what is the meaning of this tower? What is the resolution? I mean, in quantum, in field theory, in the end, you can resolve everything. Like all the singularities somehow is about a new light state that appear, and that's why you have a singularity. But you can resolve it. And we can understand in string theory what is the meaning, what is the interpretation of these towers. And so far, there are just two possibilities, which makes it simple, much simpler in the end. So let me just tell you the two possibilities and I will finish because I guess I have to go for lunch, right? Yeah, sorry for that. So just so you know, and also you make it, I mean, if I give you the possibilities, it becomes more concrete. So the two possibilities, I mean, the two interpretations of these towers that we have found are either that this signals decompactification in some frame, some dual frame, in the sense that these tower states are like Kaluza-Klein modes. So for example, right, if I have some circle and I make this circle very big, the volume of the circle, I have all the Kaluza-Klein copies becoming large. And indeed, I get infinitely many new states becoming light. They are just all the Kaluza-Klein copies, all the right, the eigenvalues of my Laplacian on this circle. I'm compactifying a circle, so I have the zero mode, which is typically what I care about. But I also have all the other eigenvalues, which have a mass the eigenvalue of the Laplacian is proportional to 1 over the radius. So if the radius becomes very large, they all become very light. Okay, so they become degenerate. And this is the interpretation. So I have a new dimension that opens up. Okay, so I cannot continue doing physics in the same number of dimensions. I need to grow extra dimensions. Okay, so that's one of the things. So this is telling you that, yeah, one possibility is that quantum physics breaks down because you need extra dimensions, because if you go too far away, you need new states. And the other option is extreme perturbative theories. Okay, so sometimes these excitation modes, as at this tower, is associated with the excitation modes of some extended object. Like for example, when I have a string, if the string coupling goes to 0, string counts like infinite many particles in a sense with recoupled to gravity. Okay, so all these states become light, and this is telling you that you cannot do field theory anymore. You cannot just talk about particles. You need to go to string theory. You need to consider extended objects, higher spin states. Okay. And this is these are the two possibilities. So in all so this is what is called the emergent string conjecture by Timo here. Claiming that these are the two only possibilities that we have found in string theory, but then has been proposed that these are the only two possible in quantum gravity in general. And it's kind of, I think it's quite cool because like understanding these infinite distance limits is like understanding what are the possible quantum gravity theory that you have. It's like, this is telling you, okay, when your QFT breaks down and quantum gravity become important, what quantum gravity I get, okay? What are the features of these quantum gravity theories? So far, yeah, all the universal features that we found is that either you need to consider string theory, like the theory of strings, or you need to consider extra dimension. And this is what this is physics that appear at this infinite distance. But it's very important, yeah. So most of the work is like first trying to prove this, trying to prove that you have these states, which we'll see. You will hear more about this actually in 2 weeks because this is more about the second part sometimes. Sometimes we have shown also that using, like in Calabi-Yau manifolds, we could prove this using the theory of Hodge theory, because then Hodge theory relates both. We can compute the masses and the geodesic distance and the metric with the same quantities, which are the periods, and by Hodge theory, we can see that there's a universal form of the periods such that this is always realized. So it's really about some universal properties of Hodge theory that this works. So you have to prove this, and then you have to understand what are the resolution and what is the meaning, the interpretation of the tower, what is the nature of the tower. And for this, it also becomes again very important to count the states and understand where they're coming from and on these modular forms. This is where the work is done. I try to understand what is the nature of the tower, what are the possibilities, and try to prove that this is a general thing beyond string theory. So I think I'll stop here.